This subunit is labeled intramolecular force and potential energy in the CED, but really it's just about the potential energy of atoms as they come closer to one another. So in this video, we will dissect potential energy versus intermolecular distance graphs in order to understand what these graphs tell us about the formation of bonds. We will also use Coulomb's law to quantitatively explain the relative strength of bonds. And I want to do a quick disclaimer before we start. This unit is labeled intramolecular, and the graphs we'll be talking about, the x-axis has a unit called intermolecular. Just so you know, intramolecular forces are going to be forces within a molecule, and intermolecular will be concerned with between many different molecules. But now that we have that out of the way, let's get started. Let's start with a very basic question. What do potential energy versus intermolecular distance graphs show? Simply, they portray the forces of attraction between two particles, which could be atoms or molecules, depending on the context. The x-axis of these graphs is the intermolecular distance between two molecules, oftentimes in picometers, though units may vary. As we move from right to left, this value is decreasing. As you can see, it goes from 200 back to 0. So we can say that the two atoms are getting closer to one another. The y-axis of these graphs show the overall potential energy of the system, commonly in kilojoules per mole, although again, the unit may vary. Now that we know what these graphs show, let's answer the following. What do we use potential energy versus intermolecular distance graphs for? Mainly to understand how bonds between atoms form. Let me walk you through reading this graph so you can better understand how it's used. And I'm simply going to walk you through absolutely all the information you can derive from looking at this graph. As you can see, we have 4 stages. Each stage has 2 atoms in it, atom 1 and atom 2. In stage 1, these atoms are a distance of slightly more than 200 picometers apart from one another. And the overall potential energy of these 2 atoms is close to 0. In stage 2, as denoted by these arrows, the atoms have begun moving closer towards one another. This could be for a variety of random reasons, but all we know is they are approaching. The distance between them has decreased to now under 200 picometers. And if we look, so has the potential energy. It is now nearly negative 250 kilojoules per mole. This continues into our third phase, where the atoms are very, very close to one another, just under 100 picometers, and their potential energy has now reached its minimum, around negative 400 picometers. This point that I'm circling right here is known as the equilibrium bond distance. At this lowest point, the attractive and repulsive forces balance out. This is where a stable bond will form, when the potential energy between the two atoms is at its lowest. Moving on, however, we come to stage 4, where we see a very interesting reaction. The intermolecular distance between the atoms has once again decreased. Now we're closer to around 20 picometers. However, the atoms have moved too close to one another, and so they will now begin repulsing one another. This repulsion will rapidly increase their potential energy, and the bond will break. And these atoms, as denoted by the arrows, will move apart from one another. One last thing I want to show you on this graph is our 3 regions, which you can kind of already derive from the walkthrough I've just showed you. We already know about the equilibrium bond distance, but there's 2 more. The first region is the attraction region, and this is pretty self-explanatory. It's just where the 2 atoms are being attracted to one another. And the second region, as you might have guessed, is the repulsive region. Opposite to the attraction region, this is just where the 2 atoms are repelling one another. And then, of course, our third, like I said, we've already gone through it, is the equilibrium bond distance. This is where the bond forms. This spot right here, I want you to drill that into your head. Where the potential energy is the lowest, the bond will form at this distance. So, that is what we would use a potential energy versus intermolecular distance graph for, to understand how bonds between atoms form. We can closely follow our curve, seeing how as the atoms get closer, their potential energy changes, and we can denote the exact distance at which a bond will form. Before I move on to the factors that can affect our curve, I want to make one thing abundantly clear, which you might have already derived from this walkthrough. The deeper our curve, or the smaller our potential energy value, the stronger the bond. I really, really, really want you to write this down, star it, jot it, underline it, highlight it, whatever you need to do. You need to know that the deeper our curve, the stronger our bond, because there is less potential energy between the two molecules. They are more stable with one another. And the inverse is true as well. The higher our curve, or the greater our potential energy value, the weaker the bond is. So again, the deeper the curve, the stronger the bond. You gotta know that. Now that we know how to interpret these graphs, what factors will affect their curves? Firstly, the charged magnitude of each atom. And to fully explain this to you, I'm going to employ Coulomb's law, whose equation roughly reads the force of attraction between two particles is approximately the charge of the first particle, Q1, times the charge of the second particle, Q2, divided by the distance, r, between them squared. As you can see by this equation, if the charge of the atoms is increasing, then the force of attraction will also be increasing. The second factor which can affect this curve is the polarity of the molecules. The greater the difference in electronegativity, the more polar the bond, and generally, the stronger the interaction. This results in a deeper potential energy curve. We already know this from dissecting ionic and covalent bonds. Ionic bonds are stronger because the large difference in electronegativity allows them to transfer a full electron, whereas the less polar difference in covalent bonds means that electrons are only shared. If this doesn't make sense, or you haven't seen those videos on my channel yet, I highly recommend you check them out. This also means that the type of interaction between the atoms will affect the deepness of the curve. The stronger the bond we are forming, the deeper the curve. So covalent bonds would have much deeper curves than hydrogen bonds, which would have deeper curves than London dispersion forces, and so on. A last factor which affects our curve is the atomic radius of our atoms. Let me use an example and Coulomb's law to show this to you. Let's imagine we have two atoms, a small one and a small one. The distance between their nuclei will not be very large. But now let's say we have a small atom and a very large atom. Well, because the large atom is large, the distance between their nuclei will be large. That makes sense. So if the R value in Coulomb's equation, or the distance between the two atoms, is increasing, since that's in the denominator, our force of attraction must be decreasing, which is why the larger the atomic radius, the smaller the force of interaction, or the less deep our curve. And so those are our main factors which will affect the deepness of our curve. I know I said it earlier, but I just want to repeat it so that you can really get it drilled into your head. The deeper the curve, the stronger the bond. To finish off this video, I want to discuss one last instance which will change the depth of our curves, but which I think deserves its own category. And that is the bond order which the atoms are forming. Bond order is a measure of the number of chemical bonds between two atoms. That basically just means, are the atoms forming single, double, or triple bonds with one another. This graph shows several potential energy curves for different carbon-to-carbon bonds. While each one of these curves involves a bond between two carbon atoms, each bond has a different bond order. Remember that the deeper our curve, the stronger our bond. Another rule that I want you to be familiar with is the following. As bond order increases, the bond becomes stronger and shorter. This is why the curve gets deeper and steeper as the bond order increases. And this obviously makes sense. A triple bond is going to be much stronger than a single bond. It's going to hold the two atoms closer to one another and have a lower potential energy. So looking at this graph, what I want you to be able to tell is that the blue curve is a first order bond or a single bond. The red curve is a second order bond or a double bond. And the purple curve is a third order bond or a triple bond. You'll never really go above third order in your chemistry class. I also want you to clearly understand that the purple bond is going to be stronger than the red and the blue bond. And the red bond is going to be stronger than the blue bond. After watching this video, you should now be able to interpret potential energy versus intermolecular distance graphs and correlate their curves to the properties of a molecule's bonds. You should also be able to use Coulomb's law to explain why some atoms form stronger bonds than others. As always, if you're struggling with this, try rewatching parts of the video. If you're still not getting it, just take a break and come back later. This will click eventually. Thank you so much for watching.